as an example of modification of a property of a composite material due to addition of reinforcement, let us consider Young's modulus of a composite material. Young's modulus, particularly for example, we looked at polymer matrix composite, the glass fiber reinforced plastic GFRP. So, in this the polymer itself has very low stiffness, very low Young's modulus, but glass has higher stiffness. So, when glass is added, the stiffness of the composite, the Young's modulus of the composite increases. Two standard models are used for calculation of the Young's modulus. One is the isostrain modulus and another is isostress modulus. We will look at both of them. Let us look at for the isostrain modulus. A good model is of continuous aligned fiber composite. So, in this sketch I have shown a sketch of continuously aligned glass fiber composite. So, the polymer is of shown as a block of length L and the fibers are also of length L running from the left end of the composite to the right end. So, these fibers are of the reinforcing phase. So, they have a different modulus, the modulus is EF, whereas the modulus of the matrix is EM. Also, the volume fraction of the two phases is important in determining the modulus of the final composite, and the volume fraction of fiber, let us call that Vf, or much more simply as, let me denote it as F. The volume fraction of the matrix is Vm, which will obviously be 1 minus F, because there are only two phases. So, the volume fraction of matrix is 1 minus the volume fraction of fiber. On the cross sectional area, a part of the area is taken by the fiber. These areas are taken by the fiber, whereas rest of the area is taken by the polymer. The rest of the area is the polymer area. So, we can, if we so wish, separately denote the area of the fiber as AF and the area of the matrix as AM. So, the overall area of the composite AC will be sum of these two areas. Now, let us look at what we mean by this isostrain loading. So, for such a composite, if I put a load, Fc on this composite material, then this load will be distributed on the fiber and in the matrix. Let us say that in the fiber the force is Ff, that is the sum of not on just this fiber. By Ff I mean the sum of the forces acting on the entire cross section given by the fiber, and similarly on the matrix there is a force Fn. So, obviously, this Fc will be the sum of these two forces. So, the total force on the composite is sum of the force on fiber plus the force on matrix. Now, let us look at, due to this force, what extension the composite undergoes. So, let us say that there is an extension extension delta L due to this force. The original length of the composite was L. So, you can also see here that the original length of the composite L C is same as the original length of the matrix and the length of the fiber. All of these are same, and so we are designating all these equal lengths by L. Similarly, if there is no debonding between the fiber and the matrix, the fiber will also extend by the amount delta L and the matrix will also extend by amount delta L. So, the change in length delta L in the composite, changing length of the matrix and changing length of the fiber, all these quantities also are same, and let us call them that as delta L. So, this of course leads to equality of a strain in all these phases. So, strain in the composite is equal to the strain in the matrix is equal to strain in the fiber, all of which is equal to change in length delta L divided by original length. So, let us call all these strains as by a single symbol epsilon. So, this is the reason why we are calling this loading as an isostrain loading. So, this results in an isostrain loading. So, for this isostrain loading we have seen, let us begin with the force. We saw that the force on the composite was sum of the force acting on the matrix cross section and on the fiber cross section. Now, since we are interested in stress, we will divide it by the composite cross section F c by A c. A c is the entire cross section, this entire cross section on which the force F c is acting. So, we write it as F m by A c, F f by A c. This can of course be changed. This we can call this force on the composite cross section by the area of the composite cross section is the stress in the composite cross section, sigma c. So, sigma c is stress in the composite. So, this will equal to, now F m by A c does not simplify to anything known. So, I write it as F m by A m, which will become the stress in the matrix. So, I have to then multiply it by A m by A c. Similarly, I write this as F f by A f into A f by A c. So, sigma. Now, this can be simplified into F m by A m can be written as sigma m, and I multiply for this fraction, I multiply the numerator and denominator by L to convert them into recognizable volumes. Similarly, F f by A f is sigma f, and then I have A f into L by A c into L. So, sigma m is stress in matrix and sigma f is stress in fiber. Now, you can see this can further be converted into what is this quantity, say AML. AM is the cross sectional area of the matrix and it is being multiplied by the length of the matrix. So, AML is the volume of the matrix, whereas ACL is the volume of the composite. So, we are dividing the volume of the matrix by volume of the composite. So, this is nothing but volume fraction of the matrix. This is nothing but volume fraction of the matrix plus sigma f, and similarly this is nothing but volume fraction of the fiber. So, we finally get a very simple and interesting relation that the stress in the composite is just weighted average of the stress in the matrix and stress in the fiber, with weighting factors being the volume fraction. And if I use my symbol F for Vf, I can write this as sigma m 1 minus f plus sigma f into f. But we are interested in the modulus. So, I write stress as modulus of composite times strain in the composite, but strain in the composite we have seen is strain in the composite is strain in the matrix and strain in the fiber are all same and is equal to epsilon. So, I write it as epsilon. Similarly, sigma m I write as E m into epsilon 1 minus f plus sigma f as E f into f, sorry, E f epsilon into f. So, this epsilon of course cancels out from this equation, finally leading us to a relation identical to the stress, that E c is nothing but 1 minus f times E m plus f times E c. Again a rule of mixture or weighted average kind of formula for this modulus also. So, let us look at how does that modulus look like. So, the composite modulus is 1 minus f times modulus of matrix plus f times the modulus of the fiber. Now, here I am trying to plot with x axis as the fiber volume fraction running from 0 to 1. So, at 0 volume fraction of fiber you have pure matrix, and the pure matrix has a modulus E m. E m is the modulus of the matrix. And the pure fiber at volume fraction 1 you have only fiber. So, the pure fiber has a modulus E f, and if you plot this, this is nothing but a equation of a straight line running from E m to E f. So, all you get is a straight line joining these two points. So, this is a nice simple relationship, and this is based on the isostress loading. When the isostrain loading, when the strain in the fiber and composite and the matrix are all the same. So, this is the isostrain modulus for the composite. In a typical glass fiber reinforced composite, for example, let us say GFRP, EM will be very low, let us say 1 to 2 gigapascal. So, this may be 1 gigapascal, whereas the glass EF has a very high modulus, so 70 gigapascal. So, you can see that in this formulation EC, let us say for 50%, for the 50% composite, EC will become 0.5 EM plus 0.5 EF, which will be 35.5 gigapascals. So, by putting 50%, by 50% of the reinforcing glass fiber, we can raise the stiffness of matrix, which was very low, from 1 gigapascal to 35.5 gigapascal, which is a very high value. However, even if we required a high stiffness, we do not want the brittleness of the glass. So, composite overall is giving us a better property, in the sense that we have a stiffness, a very high stiffness, which could not have been obtained in plastic, but at the same time we are avoiding the brittleness of glass fiber. There are several glass fibers. So, if any glass fiber in the matrix, even if it breaks, the other glass fiber will still remain intact, and the whole thing will not break as a brittle material.